Hello and welcome to one more day of the Advent of Code 2022. Yesterday it was a pretty terrible day. I spent almost 2 hours or more than 2 hours recording this video, both coding and refactoring the solution. Then I found out about some other solutions that were much better than mine. Simpler, faster to code especially. But well, this is what is good about the Advent of Code, right? About solving problems in general. You spend a lot of time solving the problem, you think of the best way, and then when you really find another solution, you see the code of someone else, then it really hits you. It really opens your mind of what you could have done better, how you could have improved, and you really appreciate the solutions that the others have written. If you went directly to see the solution of someone else instead of going through the process, that is why I'm recording the whole process of me reading the statement and then coding and so on. Because then is when you can really appreciate what it takes to write that code, right? If you go and check the solution, you can say, okay, yeah, that solution looks very fine, looks very good, but you're not really learning, right? When you have put the time and the effort to solve it, and then you see a better solution, that's when you really learn. Okay, without more hesitation, let's see the 8th problem of this Advent of Code 2022, and let's hope that today we can be a bit faster. Okay, the input is the statement is pretty short today. That is good. And here we see a list of numbers. Okay, let's copy this 8.in. These are lines. So it's not a long number, but they are numbers in a list of 9. So here, let's see how many trees are visible from outside the grid. Okay. First determine whether there is a young tree cover. So these are trees, I guess the number is the height. The elves have already launched a quadcopter to generate a map with the height of each tree. Each tree is represented as a single digit whose value is its height. Okay. Where 0 is the shortest and 9 is the tallest. A tree is visible if all of the other trees between it and the edge of the grid are shorter than it. Only consider trees in the same row or column. That is, only look up, down, left, or right from any given tree. Okay, this looks pretty easy. All of the trees around the edge of the grid are visible. 9 trees. Okay. Well, I think this is pretty easy, but let's see if I am right. So what I think we need to do is we need to count the visible trees from every direction, from any point in the edge, right? So we could say, we have 4 directions. So, for example, let's start from left to right, right? So here, let's first read the input. So what we can do is open 8.in .read.split lines. Okay, so this is the grid. Are all of these lines. So what we can do is from left to right, we could do for line in grid or for row in grid. For I in range. So let's see. We could say current is the row 0, right? And let's have P1 is the solution. And here P1 starts with 1. So the current is the row 0. Then we could do for range from I to length of row 0. To the length of the row. We could do if. Let's change this. The current is -1. We could convert all of this to integers, which maybe makes sense. I don't know if we really need it. Well, no need. Okay, so let's forget about this. So what we're going to do is I character in enumerate row. Okay, so what we're going to do is if the character or the order of the character is, which is the ASCII code, is greater than the current one, then p1 plus equals 1, and current one is the ord of C. Let's print the p1 and let's read the example first. So we are going to edit 8.example. We're going to copy this example. So Python 8.py 11. So 11 means that here we see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I think this is right. So what we can do is we can do the same right to left. And instead of doing this, we iterate the row in the opposite direction. Then we can do the same top to right. Sorry, top to bottom. Or top, and then the opposite. So bottom to top. Okay. So top to bottom, instead of doing this, what we need to do is we want to, I think there's a way, if I'm not wrong, of doing zip/grid in which you transpose, and we can do the same here, zip/star grid. So AOC, Python 8. The solution here says 38, and here it says 21. So maybe we are not doing this correctly. 6 trees visible on the edge, 5 visible in the interior. Total of 21. Okay. So top left, if all of the other trees between it and the edge of the grid are shorter than it, only consider trees in the same row or column. That is okay. So here it says the top left 5 is visible, the top middle 5, the top. Oh, but we are counting trees twice. So the same tree, the same tree is visible in different places. So what we could do is trees equals a list, and instead of summing, so let's say visible. So here we could do visible dot append. Okay, so here there is one issue here, which is here we would do enumerate. So we want to keep track of the coordinates. So we are appending ij. Here, this is the same thing we need to do here. And here we want to do j enumerate. So we're going to iterate first. This is not row, this is a column, in fact. So here we could say column, and then this is I, and this is j. So what we want to do is we're going to paste this, and we're going to print the length of the set of visible. So all the different trees that are visible. 19. Okay, this is not right either. It says 21 here. So we got something wrong again. Okay, because when we are iterating from the end, this is not j. We need to print the length of row minus j minus 1. And here, when we are doing it in the opposite direction, it is the length of grid minus I minus 1. 21. Okay, let's jump and try to submit this number. No, it's not the right answer. Okay. It's the right answer for someone else. Okay. We got something wrong. Let's see. We could try to... How many trees are visible from outside the grid? So let's see. Let's print the visible and run this here. Okay, we could do it with the example too. So 0, 0, 0, 3, 0, 4. It's weird that we, yeah, 0, 0. Let me read the code, because I think we are in the right direction. We're doing it more or less right. So here, this is the length of the row minus j minus 1. Because we're iterating this row, length of the row minus j minus 1, length of the grid minus I minus 1, j column for IC in column the opposite, greater than the current. The current is the ord of C. Okay, IJ. How many trees are visible from outside the grid? I was thinking that this was right. So IJ, top to bottom, J zip grid, enumerate zip grid for IC. Oh, wait. Why are we doing this in the opposite direction here? This doesn't make any sense. This doesn't make any sense. So what is the problem now? Line 11. Okay. That was weird. I don't know why. What again? Okay. That was weird. I don't know why I had this in the opposite direction. Let's submit this. Okay, we got the gold star. Okay, so I messed up something. I was copying and pasting, and I messed up something. Now let's check the second part. Content with the amount of, okay, here is, what is the highest scenic score possible for any tree? Okay, what is the scenic? A tree's scenic score is found by multiplying together its viewing distance in each of the 4 directions. For 3, this is 4. So 5 is looking, its view is blocked by 2 trees. Possible for any tree. Okay. Let me understand again what this means. Let's consider this 5. Looking up, its view is not blocked. It can see 1 tree of height 3. Looking left, it is blocked immediately. It can only see 1 tree. Looking right, 2 trees. Looking down, 2 trees. A tree's scenic score is found by multiplying together its viewing distance in each of the 4 directions. Okay, so how much it can see, right? However, you can do better. Consider the tree of this one here. Looking up, it's 2. It's blocked at 2 trees. Looking left, it is not blocked. It can see 2 trees. Okay. Looking down, 1 tree, and so on. Okay, so we want to see how many trees each tree sees in its direction, right? So we want to go... I think we're going to do this in a separate way. So we're going to do for I row in enumerate grid, we're going to for j c in enumerate row. So we're going to do this for every tree, and we're going to compute the max. So p2 equals 0, and we're going to find in all 4 directions what this scenic score is. So what we're going to do is the height or the current one, let's say, is the order of C, right? So this is the height of these 3. So we're going to go in all directions. So for new I in range from I0 minus 1, so we're going upwards. If current, however, I wonder if these 3 can be seen or not. Is blocked eventually, it can see 2 trees, one of height 3 and then one of height that blocks its view. Okay, so that is important. So here it can see only 2. It cannot see this last one here. So what we want to see is how many it can see in each direction. So how do we do this? We want to find so let's say max sin is 0 and the current one is this. So for each of these elements, what we want to do is we can say if grid nij is less than the current one, and so if this height is less than the current one and it is less than the max sin, then the max sin equals this one. In fact, this doesn't need to be the less than the current one, right? If it is blocked immediately, you see 1 already. So what you have to check is the max sin only. So if this is less than the max we have seen, then the max sin is this, and we increment 1 to the multiplier. Okay, so let's say we're going to have multiplier 1, multiplier 2, multiplier 3, and multiplier 4. So m1, m2, m3, m4 equals 0, 0, 0, 0. So here we're going to say multiplier 1 plus equals 1. So what we're doing here, going up. Okay, so now if we're going down, we are starting from I plus 1. Instead of starting with I think we have to start with I minus 1. We start with I plus 1 until the length of the grid. And we do this, but here we increment m2. So now let's say if we go right, it is j, it is the new j, this is I, this is the new j, and this is the length of the row. If this is sorry, but the max sin needs to be updated every time. So if the new j, the max sin is the ni and the new j, and the m3 is increased. And now let's take this one here left. So if we go left, it is j minus 1 till 0 minus 1. However, this 0, I'm not sure if we do a range until 0, this is going to work. So list range 10, 0, minus 1. No, because we're not getting the minus 1. So sorry, the 0. So here we have to put minus 1. Okay, so now the grid M4. So we are going to print M1, M2, M3, and M4 multiplied. I think we want to check the example first, because we'll be lucky if we hit it. Okay, so here this comparison this comparison is not working because we need to compare with the ASCII number. Or we could compare characters too, I think. We might want to do that when we refactor. So here, or okay, 0. This is not good. Okay, because maybe, so if you're in the edge, I guess. Okay, but no, but this is not true. So this comes here. And then P2 is the max of P2, and M1 times M2 times M3 times M4, and we are going to print P2 because we want to take the maximum. Okay, still 0. So M3, M4, so let's print I, J, M1, M2, M3, M4 for the example. Okay, everything is 0. So what are we doing wrong? Okay, it's never seen. Okay, if this is larger than max sin, I think we want to do exactly the opposite. However, what? Line 57, ord larger than max sin, int and str. But max sin, okay, because max sin needs to be the ord too. Let's say, well, let's do that for now, but we want to save this as a variable for sure. Ord here, ord here, ord here. I'm wondering if there's a case where this is not, okay, 12. And here it is 8. Okay, but maybe 12 is the maximum. So let's try to submit this. Otherwise, we will debug a little bit more. 560. No, it is too low. Okay, so it is too low. That's weird. Because I wonder if here, after this tree, do you see this tree? So looking left, it can see 2 trees. Okay, yeah, it can see 2 trees. And going right, is this just a matter of less than or equal? Maybe yes. Maybe yes, maybe not. 13,200. Okay, let's see if this is the issue. Oh, there is something else. Too low, still too low. Okay, so let's look at the example and see if we're computing this right. So we could say here, if I equals 0, 1, 2, 3, and j equals 0, 1, 2, this is the one that we see in the example. So, and here it says 2, 1, 2, 2. Here it is 2. Well, but this is top, up, it is 2, down, it is 1, 2, and 2. So this is correct. Let's check this one here, which is 1, 2. So if we check 1, 2, it says up is 1, up is 1, down is 2, 2 right, and 1 left. So this is right. A tree's scenic score is found by multiplying together its viewing distance in each of the 4 directions. For this tree, this is 4. However, you can do better. This tree's scenic score is 8. This is the ideal spot for the tree house. Okay, but we say that we are seeing one that has 12. So if this is really the ideal, then we are doing this wrong. So if, let's say, mult equals this. So if mult equals 12, print ij. Okay, 2, 3. So 0, 1, 2, 0, 1, 2, 3. This 3, it says it has 12. So if we look up, I think it is 2. Down, well, maybe you do not see the 9 because the 4 already blocks you. So I was doing something right before and then I removed it. So I think if you look down, the 4 already blocks you. So I would say, I think we have to add an other if and say if this is larger than the current one, then the max seen is already, let's import this from, well, let's say is 1 and 9 zeros, right? So I think with this, now we have an 8. I think this makes sense. In the past, I had removed this kind of check. Okay. Let's check this one. It's too low, still too low. Okay. What is the highest scenic score possible for any tree? Of course, now it is too low and I limited it a little bit more. So here, let's read the statement again. To measure the viewing distance from a given tree, look up, down, left, and right from that tree. Stop if you reach an edge or at the first tree that is the same height or taller than the tree under consideration. Okay, so stop if it's taller or equal to the tree under consideration. But stop means let's see. If this is, maybe this is an elif or not. Or not. No, this is the same. So the point is, let's see. If this one that we're checking is bigger than this one, okay, we need to, in fact, what we need to do is we need to break. And we need to increase 1. I don't know if this is exactly what we want to do. Let's think a little bit more. Let's think a little bit more. Oh, wait. So this is 4, 3, 2, 1. Okay, let's be careful with this copying and pasting. Okay, so this is even worse because this is a smaller number. We need to make it bigger. So the thing is, if it's a tree in the right on the edge, at least to measure the viewing distance from a given tree, look up. If a tree is right on the edge, at least one of its viewing distances will be 0. Okay. Don't care about distant trees taller than those found by the rules above. Okay. So the rule is look up, down, blah, blah, blah. Stop if you reach an edge or at the first tree that is the same height or taller than the tree under consideration. Okay. So I think I'm not doing this right. This is the max sin doesn't matter. The maxim doesn't matter. The only thing that matters is that this one is bigger, is larger or not. So I think we need to do this, and that's it. If this is the case, I was complicating things unnecessarily. Let's see if that is right. Okay, the number is bigger, definitely. It seems crazy big. I'm not sure that is what we want. I'm not sure that is what we want. Well, it says 8, so maybe that's what we want. Okay, let's submit. No. Okay, that seemed crazy high. So okay, this is wrong. Because this is the new J, and this is the new J. So that is definitely wrong. This is the problem of copying and pasting. That's why you don't want to do copying and pasting. Okay, we'll have to wait. Oh, you have 5 minutes to wait. Okay, I think we'll have to start refactoring instead of waiting. So let's check the input again. So here, I thought that the time that you had to wait was only 1 minute, but it seems it's more. So to measure the stop if you reach an edge or at the first tree that is the same height or taller than the tree under consideration. So we just need to end. If this one is taller than the current one, then we break. Okay. I'm curious if we can just compare. Well, let me keep this, but can we just compare this, comparing characters, and see if this leads to the same output? Yes. So this is another simplification we can start doing. We can remove all these ASCII conversions. CR. Regarding the multiplication, we could also, well, let's see. Okay, so we are the maxim. Okay, so the maxim we can ignore completely. We're not using that. And this mult, we're not using this either. So the idea is that ny n+1 if this is break. So what we can do is probably, I mean, I don't want to refactor too much before solving the problem, right? So this is a small limitation we have, but what could we do? We could say, so this is the number of elements in this direction that are larger than, that are smaller than the current tree. So I was worrying of a more elaborate problem. That imagine you have a tree that has 7, and then you have 5, and you have 2. So the point is that I thought that from after seeing the 5, you could not see the 2, but yeah, you can apparently. So if grid ny greater than c, okay. Okay. So how else can we improve this code? we could have some kind of function. So def so let's say viewing distance for I, j, int I, int j, let's say. So you would start new I equals I plus int I. So we could say new j equals j plus int j, and you would say while new I is larger or equal than 0, and new j is larger and new I is less than the length of the grid. And I'm curious if the grid is a square or not. So let's read the input in this way. Length of grid 99, length of grid 0, 99. Okay, so it is a square. So we could say, for example, n equals length of grid, to simplify and not have all this length. So we could say we want nj to be greater or equal than 0 and nj less than n2. So while this is true, ny is going to be incremented by int I, new j is going to be incremented by int j, and then we're going to say if the grid ij is equal to is larger or equal, we're going to do while this, and the grid new I, new j, so this is less than grid ij, then we're going to sum one. Red is 0, red plus equals 1. I think this is not exactly right. I think we could have an if here better. If this tree that we are seeing is larger or equal than this, we return. No, not exactly, because we want to. So what we are checking is that if while all of this is true, and if this is equal, we have to simplify these conditions later. If this is equal, break. So we are counting this summing these two, we need to do it. The other thing that we could do is we could sum here in the beginning. So first we sum. No, but we cannot sum and then check. So we have to sum it first and then check. Okay, so I think this is right. Let's try to submit this number again. I don't know if the time has passed. Okay, gold star. So we got the right solution. So now let's try to refactor this. Assert p2 equals this number. Assert, so let's say this is p1. So p1 assert p1 equals this number. So if we run this, the assertions are working. So now what I want to do is I want to make m1 is the viewing distance of ij minus 1, 0, and forget about this. Let's see if this works. It works. And m2 is I1, 0. It is not working. Okay. Oh wait, because I'm modifying this. Okay, it's working. So again, m3 is ij 0, 1, and m4 is 0, minus 1. So now we're going in all 4 directions. If I'm not mistaken, since Python 3.8, I think it's from math import prod. So you can do prod of 1 to 3. Is that right? No, I think it takes a list. Okay, so basically what we can do is we can say score. What is this called? Scenic score, right? So scenic score equals, so from math import prod of this list. And this is the max of 2 and the scenic score. Okay, the assertion works, so we can forget about this. So there is even a better way, I guess, because what we're doing is we're computing this prod and then we are doing a max. So I think we can do this in a single line, right? So the P2 is the max of the scenic score, so of this prod, sorry. So this is, I think I will delete it. So for this, even we can forget about this row and this j. So the only thing we are doing here is for j in enumerate in range, sorry, n range n. That's what we're doing. We could even do some kind of permutation or something. So for ij in product, but maybe this is unnecessary. So basically we got to have this max of checking the viewing distance for each position, giving different increments. So we could even reorganize this, so we always have the -1 and then we have the +1. So I think this is pretty good. We could check, we could refactor this viewing distance probably. I don't like that here we have this equal and here we have this less or equal. But I don't know how to do it in a better way. So we could maybe have a return instead of a break inside of this. So let's see. What we are doing is we are always incrementing this. This is, of course, this is necessary. We need to increase this before checking in the while. We could also do a for, but for with a range, but the ranges have the problem that we don't see, that we don't have what the end of the range is, because the end could be either 0 or n or -1 or n. So I don't know, this, I think this kind of works, but I still feel we could do a little bit better. So if this is equal, we break. But we cannot have this, because then we're not counting the last one. We're not counting the last one. So I think we'll leave it like this for now. And now we can refactor also the first part. So the first part, we can remove the example. We can do this. We can read input. So the visible is this. So again, we can forget about this ORD. And here, the problem with the ORD is that it's helpful because here we have 0, and we need one digit or an ASCII character that is less than 0, the number, right? If we did this, would this work? Let's see. I'm not sure you can compare. No. So we should check the ASCII characters, right? So is this, so this is not, it's more than 0, right? We could take, I don't know, the dot. Okay, the dot is less than 0. So one thing we could do is have this dot, right? So the dot will be overwritten. So I don't think this is ideal. I think we're going to refactor this too later, but let's start with this. So now we can get rid of all these ORD things. So there are some extra functions that we're getting rid of. Okay. Okay. Of course, we could also make the visible, instead of being a list, it could be a set. And instead of append, we could use add, and we just need to get the length. So we don't need to have a list and then convert to a set. Okay, this is a dictionary. Okay, because when it's empty, we need to do this set. Okay, so now this is already a set. We could also then, let me remember what we were doing in the first part, because I almost forgot. So what we are doing is we are counting how many trees are visible. This would be even the same as saying that the viewing distance is, I mean, we could almost use this viewing distance. You know, how would we use this viewing distance? So we would use this in the following way. So let's try to do a new implementation of using this viewing distance. Okay. So let's say if the viewing distance equals I, which means that you can go from I till the beginning and you reach the end, or the viewing distance going down is equals n minus I, maybe -1, I'm not sure. -1, I guess. Or the viewing distance equals j, or the viewing distance equals n minus j minus 1. We do this and we do this, then plus 1, right? So we're going to sum this for I in range n, for j in range n. alternative is this. Let's print the alternative. This is not right. It is a larger number. So do we need to get rid of this -1? I'm not sure. No. But I think this is more or less what we want to do. So if I equals this, n minus I minus 1, j is this exactly the same or not? Because in the viewing distance, I don't know, it seems like it should be, right? It seems like it should be. If we do this with the example, well, the assertion is going to fail. Cert. I think it would be pretty beautiful to have the same, to use the same function. It says 22 and it was 21. So there is something wrong with this function. So if it is the viewing distance, and the viewing distance is stopping when there is a number, when there is a tree that is smaller, that is equal or larger, which makes sense. So if we're in the edge of the, well, let's do some debugging. So if ij, so if all of this, if all of this and ij not invisible, print ij. Is this correct? Doesn't seem, because it doesn't, there's an indentation error. So, okay. 3, 1. There is one that doesn't match. So the 3, 1 in this example is 0, 1, 2, 3, 1. The 3. Okay, so the 3 is not visible because the distance, well, it's clearly not visible, but here it will say distance 1. So 1 minus 1 is 0. So the problem is that this one reaches the end, but is not really seen. The opposite would be this one here. So this one also has 1, but it is seen. So we could modify this one. So we could say include equal true, and if not include equal, red minus equal 1. And if we used this with false, okay, then we still have 22, but because we're doing it here, but it would be false, 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 sorry, false. 21. Let's run it with the input. Okay, that's the right number. Okay, so I think we're going to do that. I think we're going to go with this. Now let me explain this a little bit more. But this debugging that we did was useful. So we can remove this and we can say P1 is this and P1 is here. We forget about all of this. We add the input to the top. And this is working. Okay, so this function, what we did here, part 1, part 2, what we did here is what we calculated the viewing distance, including the equal or not. So here we do not include the equal. So how did we compute the first part? Well, we summed the number of trees, so we iterated through both I and n, and we checked if the viewing distance equals the end of the, so if we are going to the left, if we have a viewing distance till the edge, till the edge, till the edge, and till the edge. So that is what we did. Can we simplify this? For sure we can simplify this. One thing we could do, for example, is we could use, instead of using inc I, inc j, we could have incs are this list or tuple of 1, 0, minus 1, 0, 0, 1, 0, minus 1. So we could have this, and then this would be inc 0, and we could also say nj equals this and j plus inc 1. So what did we gain by doing this? Well, what we could do now is we are summing. Well, maybe in this case it is not so useful. So now we should call this with some extra parentheses, which might seem that we are just we're not doing this. This is not so useful. Let's see. So what I wanted to do is, instead of doing this, we can have a list of viewing distance ij inc for inc in incs. Okay, inc I does not exist. We could do inc I inc j equals inc I j. I think that might be easier. Okay, so we simplified this a bit. This one is a bit more different. This one is a bit different because we need to do an OR for which we could use the any, but this is not like this function is returning. So this maybe we need another function. Viewing distance. So this one is pretty good. I don't think we can really improve this anymore. We could say, so in Python we can have this iter tools from iter tools import product. Is that right? So you could say product range n r2. No, so range 3, let's say 2. Sorry. Oh, range 3. Yeah, so you could do that. Is there a better way? Import iter tools. So if we have it here from iter tools import or import iter tools dot accumulate combinations count repeat, right? No, but repeat, I'm not sure that's what we want. Repeat times. So if we do this import iter tools dot repeat range 3 twice. So if we convert this to a list, we see this, right? So we could do this. So from iter tools import repeat. I mean, it's definitely not necessary, but it. So we do for ij in repeat range n 2. So we get sorry. Okay, what is n2? Sorry, here 2. No, this is not right. Too many values to unpack. Oh, because this is it's not a repeat, it's a zip. So I think it's more iter tools dot product what we want. But I thought it was you could repeat. Or similar to combinations, but combinations is not what we want because we don't want. We want to repeat them. So I guess instead of repeat, it is the product we want. So this is product range n, range n. Okay, we have it in one line. Maybe, so the idea is it better this in range n or this? Do you prefer this or this? I think I prefer this. We have one less import. It is a standard Python. I mean, the other is standard Python, but it is a standard library. These are built-ins, and it is shorter. So one more line, but one less import, not really necessary. Okay, so here, what we could do is maybe we could improve this in some way. It is difficult to see how. It is difficult to see how. Red. We have this include equal, which is might seem unnecessary, but it's a bit ugly. But we really need it. We really need it. We could. So I had decided to use this viewing distance for part 1. Probably there's another option, would be not to use it. So we are going back, right? So the idea is if all of the, let's start with the, so let's see, for let's try to do it directly as a one-liner, right? So we're trying to do that to see that all of the characters in the range of, so we are going to do for I in range n, for j in range n, if any, so it's if either it is visible from the top, from the bottom, left and right, so if any and all grid and I and j are less than grid ij for so, or let's say ni for ni in range I minus 1 minus 1 minus 1, so ni and j and I and j and j and j, and this is I plus 1, sorry, I plus 1 and 1, of course, and this is j plus 1 so let's alt equals this alternative. Is this going to work? No. Okay, because we're giving any what I thought was an iterator, but wasn't. Okay, assertion error. Let's print this alt. Okay, we're almost there. There's a difference of 3. So I don't know what the issue is. Oh, here we have an I instead of a J. Okay, now it works. So here we have a different way of doing it. Right? We are, instead of doing this and reducing the viewing distance, we can have this kind of sum of any. So it's, I think this is even, I don't know, we could discuss if it's more understandable or not. So here we are checking that for this ny, ny, nj, nj, so in 4 directions, we're checking that this grid n1j is the new element, that all of the elements going up, going down, left or right are smaller than this one. There is one thing we could do. Okay, let's work a little bit more. I'm not tired today, so let's work a little bit more. I have an idea of something that might simplify the code a little bit. So we could have a function which gives us let's say, I don't know, let's call it positions or neighbors or lines. How do we want to call it? Positions. I don't like this name, but let's call it positions. So for I, j, and an increment. And what we're going to do is this. So what we're going to do is take this increment, and then while this is true, forget about this, we're going to yield, this is something new we use today, ny, nj. So what this does is, given an increment, it gives us the list of trees in this going in this direction. So instead of positions, we could say indices, maybe. No, well, positions is fine. So we're getting an I and a j in each direction, right? So why is this useful? Because here, for example, what we could do, we could say ny and j is less than for ny and j in positions I, j, and the increment, which we will see now. So we want to do this, sorry, for ink in inks. So we want to see that all of these holds, sorry, okay, position. Okay, we are hitting some kind of infinite loop. Return, oh, because we need to increment this. Yeah, there's no return, doesn't make any sense. Okay, so this is right. So what we're doing here is we are checking that this grid is smaller than grid I for ny and j in positions for each increment. Let me see if we can do this. Yeah. So if in any direction all of the elements in this new position are less than or equal than this, then we can stop. Even what we don't want to see, we don't care about ny and nj. I think what we care is about the grid ny and j. So what we could do is we could get trees in direction, right? So what we could say here, this is the tree for tree in trees in direction. Okay, so that is even simpler. So and these inks, we could maybe even replace it with directions. Well, let's keep it inks. The inks are increments, right? So here what we can do is we sum the fact that the tree is smaller than ij for tree in trees in direction. So we are checking all the trees in this direction for all directions, and if any of these directions has all the trees smaller than this threshold, then we're doing this right. So let's remove this P1. Okay, so the part 1 is almost a one-liner right now. And for part 2, I suspect we can do something very similar, because now we don't need to do all of this. So the viewing distance, now we forget about this thing we did. So now what we can do is this increment. There's no need for us to do this while we are already checking this. So what we can do is while and the increment and so on. So what we can do is for trees in dir ij inc. So this is going to give us all of the trees. And what we're going to do is red plus equals 1. And then we're going to do this break. Is this right? No. Okay, so grid ny and j is the tree. Okay, no. We're not doing this. I'm not thinking straight now. Let's undo this. What we're doing here is we are taking all of the trees. So for trees, we add 1. we break if the tree not only equals, but is so. Let's say is larger or equal, right? Not only if it is. Okay, now this is right. Okay, so now this is much simpler now. So what we are counting is while the tree is larger or equal than the grid, we return this. So what we can do for tree, how can we do this? I guess there must be some iter tool or some functional programming function that we can use to make this very easy. So if we remember from iter tools dot something like accumulate or drop while we want take while, right? Take while has a predicate and iterable. So return successive entries from an iterable as long as the predicate evaluates true for each entry. So take while, I guess this is a lambda for each tree. We say that tree is larger or equal the grid ij for trees in there. Let's print. So this is if this is a list, let's print the list of L. What does this look like? Take while, okay. From iter tools, import take while. Okay, so are we returning the list, the length of the list of L? Is that right? No, assertion error. We need to take while, well, not while this, while this is less. But not exactly, because then we are not keeping we're not counting the one that is equal. If the tree is less or equal, let's print p2. So what we want to do is if we want to take the less or equal, but we want to take the equal. So I'm not sure the take while will help in this case, because we want to count one more in the case that the tree that we find is equal to the current one. So this is not so easy. For tree, return +1. This one we're breaking, but we're adding one first. So maybe we cannot use this. It's unfortunate because it looked it was a very, it would be a one-liner almost. It would be a very simple thing to do. So here what we could do What does the take while? Sorry, but take while. What does it do? Does it do? I don't know. Okay. So well, we can keep it like this. The viewing distance. Of course, we could also, instead of doing this like this, we could also do it. So P1 equals 0, P2 equals 0, and then we do for I in range n, for j in range n, and we could do both things. So P2 equals max of P2 and this product, right? And P1 plus equal this. So it's a matter of taste. It's a matter of taste. I like to separate part 1 and part 2, but here we can do only one loop through all of the list. I prefer my solution. So now let's move this viewing distance. Well, let's keep it up here. So what else is there to refactor? Okay, this I think is perfect. This I think is perfect. The only thing, this one, we could see if there's a better way of doing this. So we have to increment in the beginning, and then we have to do this while. So this we would do in a do while, right? Would be the classic thing. The classic thing that we could do. Maybe we could even. No, so first we need to increment, then we yield, and then we increment again. I don't think there is much else we can do. The inc j, we could maybe just do it like this. 0, 1, right? 0, 1, and we could say ny and j, so we could do this as a one-liner, and this would be ny and j. So, well, it's a bit more compact to do it in this way. It's a matter of taste. So here we're incrementing the first I and j, and here we're incrementing the ny and j. We're yielding the tree while we are inside of the grid. And finally, the viewing distance, we're counting all of the trees in its direction. Well, not in its direction, but in this direction. We could replace the inc with direction. Oh, sorry, no, dir doesn't work. So let's keep it with inc. Dir is a reserved word. So here, let's try to think about this function a little bit more. So because breaks are not ideal, right? We're returning 0 and we're counting this. So we need to count. We count either until the end of the for loop or the tree is larger than this. So for each tree, if the grid ij return 0 plus 1. I love the take while function, but it is not what we want to do. Okay. Well, I guess this is it. We got a pretty short code, 41 lines. Let's recap on the lessons we learned today. So lessons learned. Well, we try to use take while, but didn't succeed. But we learned about some iter tools. So we learned about some iter tools. So I tried to use let me rename this. So we tried to use take while, we tried to use product, we even checked repeat and combinations. I mentioned it. We didn't use any of them, but they are useful. Then, so here, let's remove this. We use the math.prod to get a product of a list of numbers. This, I think, was added pretty recently in Python, maybe Python 3.8 or so. Then we used any and all built-in functions, other than other ones that we already know, which are max and range, of course. So any checks a list of booleans and returns true if one of them is true, and all checks a list of booleans and returns true if all of them are true. They are very, very useful for problems like this. We used list comprehensions. So list comprehensions, we are always using them, but here we're using them heavily. So this is a heavy list comprehension. This is a sum of any for two for loops for I and for j, and any and an all and an other for loop here and an other for loop here. So this, I don't know. Someone might think that this is too difficult to understand, but I like it. So here we are summing all of the trees for which any of all these directions have all the trees under this tree. So I like it. And the same here. So we're using list comprehensions. What else are we using? Well, we're using a list of inks, increments to generalize, to move around the grid. So we use this increment in the y and x axis of 1, 0, minus 1, 0, 0, 1, 0, minus 1. This was very helpful. And then I think the most esoteric or interesting thing we used is the yield. The yield command, right? So here yield, this is a function that yields this number. So it iterates using this loop, and then it yields this value. What yield means is that it converts this function in a generator. So a generator is a function that generates numbers kind of as an iterable, and we can use it in for loops. So this is a very useful way of creating a generator. If other generators are kind of the range is a generator, and iter tools also generate this take while, product, repeat. They all are creating generators. But this one we used here, both in the first part and the second part, in these for loops, and they are very, very helpful. So, well, yield is create a generator. So these are the lessons we learned. I hope you enjoy it. I tried today I was pretty quick in solving the problem, but I tried to refactor it as much as possible and leave it as clean or as short as possible. I hope you enjoy it. Now I will go and check the solutions of other participants, and maybe I will learn many more lessons too. Have a nice day and see you tomorrow.